All right, we started off with part 2 of our prep chapter section 3, with classification and combinations of functions. First of all, polynomial functions in the form of this one right here, an x to the n, and so forth. The positive integer n is the degree of the polynomial. So normally we classify our polynomials by the highest degree. The numbers a's are coefficients, with a of n being the leading coefficient. And it's important to know that the leading coefficient, because we can do what's called the leading coefficient test, that tells us quite a bit about what a graph does. All right, we can tell at least what happens to the end behavior of a graph. We know from the parent graphs that any even function is going to look at the end at least like a parabola. All right, it can do some crazy things up in the middle, but at the very least, as x approaches infinity, y is going to approach infinity. As x gets bigger or smaller and smaller this way, or bigger and bigger to the negative side, y is getting bigger and bigger positive, so it's approaching positive infinity. So that's any even polynomial, and even any odd polynomial was going to look like the disco dancer if you remember your parent graphs. So it'll look like a disco dancer like this. Then of course, when we're talking about end behavior, we're worried about what's happening as x is approaching negative infinity, and we're worried about what y is doing as x approaches positive infinity. Well, as x is approaching positive infinity, y just keeps getting bigger and bigger, so y is approaching positive infinity. As x is approaching negative infinity, y is getting bigger and bigger negative, so it's approaching negative infinity for an odd function. So knowing this and knowing that's what our translations and all that stuff do yet, we can tell quite a bit about the end behavior of each graph. So in example 3 here, we're going to describe the end behavior of this graph y equal to 4x cubed plus 3 plus 1. Actually, I think that's supposed to be 3x, by the way. Obviously, I can add 3 plus 1. I think it's supposed to be 3x, but however, it doesn't matter. We can tell what this graph looks like by just looking at this leading coefficient right here. That leading coefficient tells us that the degree is odd, and the leading coefficient is positive. All right, since we have a positive odd, all right, it'll look just like the disco dancer, like this. Look just like a disco dancer. All right. So if we want to describe the end behavior, we'd say as x approaches infinity, so as x gets bigger and bigger this way, y approaches infinity as well, because y just keeps getting bigger and bigger that way. And then we want to describe both end behaviors, so we want to say, well, let's look at the other way. As x approaches negative infinity, y is going to approach negative infinity as well, because y keeps getting bigger and bigger in the negative direction. All right, so there's A. B, we have y equal to negative 6x squared plus 1. Again, we're going to use the leading coefficient test, and we're going to look at the highest degree and the leading coefficient of that degree. All right, the degree tells us it's going to be an even function, so it's going to look like a parabola. The coefficient, we look whether it's positive or negative, is negative, and we know what happens when we put a negative in front of our parent graph, an x squared or an even function. When we put a negative in front of it, it's going to flip it over the y-axis. All right. So we're not concerned with what's going on in the middle, but we're just looking at the end behavior. So as x approaches infinity, we look to see what this graph is doing as x gets bigger and bigger towards infinity, and y just continues to get bigger and bigger negative. So x is going to approach, y is going to approach negative infinity. Again, on the other side, we want to look at both sides. So as x approaches negative infinity, so as x gets bigger and bigger in this direction, y is going to get bigger and bigger going down, so y is going to approach negative infinity as well. Okay, if we happen to have an odd function, a negative odd function, so say this was, instead in this direction, this was negative 4x cubed, we just know it would be flipped like this, and we can describe the end behavior like that. All right, if we know our reflections from the first section of these notes. All right. And the last part, definition of composite functions. Composite functions, when we're given two functions and we put them together, f of g of x is what this stands for. f of g of x. We know from algebra days, whatever is inside the parentheses, we go ahead and we plug it in for the independent variable. So let's look at example 4. It says f of x equals 2x minus 3 and g of x equals cosine of x. We want to find f of g of x. So what we're going to do is anywhere we see x and f of x, we're going to plug g of x in. So we're going to plug cosine in. So we're going to say that f of g of x equals 2 times cosine of x minus 3. And that is f of g of x. To find g of f of x, anywhere we see an x and g of x, here, we're going to plug in f of x. So to find g of f of x, we're going to plug in 2x minus 3, anywhere we see an x and g of x. So we're going to have the cosine of 2x minus 3. So that's f of x and g of x. If we could simplify, we do that. Right here, we really can't simplify too much. As far as the next part is testing for odd and even. If a function is an even function, if we were to plug negative x in everywhere we saw an x and we still got the same function we started with, it's an even. For an odd function, if we plug negative x in and it changes every single sign in the equation, it's going to be an odd function. So example 5, determine whether each function is odd, even, or neither. Then it actually says find the zeros of the function. All right. Well, to find a here, tell whether it's odd or even, we go ahead and we plug f of negative x in and see what we get. If I plug negative x in, so I have negative x cubed minus a negative x, all right, we're gonna have negative x cubed plus x. Did that change every single sign in the equation? Yes, it did. Therefore, f of x equal to x cubed minus x is an odd function because it changed every sign. All right, let's look at b. Is that odd or even? All right, so we go ahead and we plug f of negative x in. We plug f of negative x, we have negative x to the 4th plus negative x squared minus 2. A negative to the 4th power to an even power is always going to be positive. Same thing here. Since we plugged f of negative x, and then we got the original equation that we started with, that function there is an even function. Now the second part of the equation is to find the zeros, or not the equation, the second part of the direction is to find the zeros. To find the zeros in an equation, we're just going to set the equation equal to 0. That's what they want. They want to know when x equals 0. So we're just going to say 0 equals x cubed minus x. We're going to pull an x out. So we have, because they both have a shared term of x, so we'll have x squared minus 1. So here we set both of these equal to 0. Because if this x is 0, it doesn't matter what's over here. 0 times anything is 0. If this guy right here is 0, it doesn't matter what the x is because anything times 0 is 0. So we set both of these equal to 0. So x equals 0 is one of the zeros. And x squared minus 1 is another one of the zeros. I'm going to add my 1 over. X squared equals 1. X equals plus or minus 1 because we take the square root of both sides. Square root of 1 is plus or minus 1. All right. As far as the other one, find the zeros of this function. Again, we said we're just going to set it equal to 0. So 0 equals x to the 4th plus x squared minus x, or minus 2. We can factor that down. Looks like we'd have an x squared and an x squared. We're going to have a plus and a minus. Looks like it's going to be plus 2 and minus 1 equals 0. Again, we set both of those equal to 0. If we set both of those equal to 0, we'll get x squared plus 2 equals 0. So we'll get x squared equals negative 2. x equals the square root of -2, which is going to be an imaginary number for graphing that. Obviously, we can't use that as a 0. It's not going to cross an imaginary number, not going to cross the x-axis. And on the other hand, if we set this one equals 0, we're going to have x squared minus 1 equals 0. Add 1 over. X squared equals 1. X equals plus or minus 1. Because it's a square, we're going to take the square root of both sides. So those are the zeros of your functions.